All right, so yesterday we finished up talking about our favorite friend, Victor Grignard. He was the chemist that developed this organometallic reagent where we can make carbon into a really strong nucleophile. And we said that this carbon-based nucleophile can add into ketones, aldehydes, and esters. Why couldn't we use this with a carboxylic acid? Acid-based chemistry, right? So Grignard reagents are really strong carbon-based nucleophiles, but they're also really strong bases. And we went through a bunch of examples showing how this can add into things like ketones or esters. And we said if it adds into an ester, it will do so twice. And then we talked a little bit about how we can actually prep our reagents and then plan out a small-scale synthesis. Tomorrow what we're going to do is focus a lot more on synthesis, but I wanted to finish up today with a few more synthetic tools. So let's take a look at something. And I want you guys to help me identify the problem with this reaction. Let's say I've got this aldehyde, and I want to treat this with methyl magnesium bromide, followed by some sort of weak acid. What do you guys think I'll get out of this? Won't happen? Yeah, exactly. So if we look at this, I immediately see a big problem. This big problem is we've got an acidic proton. This aldehyde proton is actually not very acidic at all. The oxygen can stabilize the negative charge a lot more than a carbon, so the alcohol proton is going to be much, much more acidic according to our Areo rules. So we've got an acidic proton, so if we do this reaction, really nothing's going to occur. You're going to deprotonate your alcohol, and then in step 2, you're just going to reprotonate it, so you're kind of stuck. So then the question becomes, well, how can we create a Grignard reagent that will add into the aldehyde without deprotonating the alcohol? And we have to use a little bit of chemistry trickery. And that is, we must use a protecting group. A protecting group is basically some sort of reagent that you add to your molecule that can be easily removed in a later step. So it essentially will block the alcohol from reacting in an acid-base manner. So let's take a look at a really simple protecting group. Let's say I've got a simple alcohol, and I'm worried about this alcohol reacting with my Grignard reagent. What I can do is react it with a special type of silane. And I'm going to abbreviate this as methyls coming off there. And in this case, the alcohol will actually do a backside attack on the silicon and then kick off our chlorine. And now the oxygen's got a positive charge. This is actually an SN2 reaction. I told you guys that SN2 reactions don't occur if that backside attack is crowded. Why do you think it might occur with silicon as opposed to carbon?
It's much larger.
It's huge, yeah. Silicon's a lot bigger than carbon. So if you actually look at the space filling model for this, the backside is a little bit more exposed than if it were a carbon with 3 methyl groups coming off, which allows this to occur in an SN2 type fashion. This functional group is referred to as trimethylsilane. Let me move this over. But colloquially, it's referred to as TMS. It's a little bit easier to say TMS than trimethylsilane all the time. You can also abbreviate it, so you can write ROTMS, and TMS just refers to a silicon with 3 methyl groups coming off. Last but not least, we typically want to deprotonate these. And in order to deprotonate this, we normally use a really gentle base, something like triethylamine. And specifically, we want to use a base that's not nucleophilic, a base that won't do any other chemistry. You just want it to be kind of a benign base that only removes protons. So this will come grab this proton, and we'll get to our final product. That's ethyl. So 3 ethyl groups coming off of a nitrogen, triethylamine. So you may see me write this either with the silicon or just abbreviate it OTMS. Either one is appropriate for this class. The nice thing about this is that this is no longer protic. It can't do acid-base chemistry. Okay, so now let's take a look at our reaction. So we had how many carbons? 1, 2, 3, 4, 5 carbons with an aldehyde. Let me make sure I've got this right. 1, 2, 3, 4, 5. There we go. So we've got our starting material. Let's assume that we want to add a methyl group to the carbonyl. All we need to do now is first protect it. So we'll write TMSCl and triethylamine. And if we do this now, we've got TMSO as our protecting group. Now we can throw our Grignard at this reagent after purifying it. And we can say, all right, we'll use methyl magnesium bromide, followed by a weak acid workup, or I'll just do water. Oops. And we'll get our alcohol out. So now we've formed our secondary alcohol. However, we've got this TMS group still stuck on our molecule, so we've got to figure out a way to remove the protecting group. And in order to remove a TMS protecting group, you have 2 options. The easiest route is actually just to treat it with H3O+, so some sort of acid. Or, for other protecting groups, the more common reagent is called TBAF. More alphabet soup for you guys. But really, all this does is remove the TMS group, and we'll get you back to your original alcohol that you had in the beginning. Oops. So this will remove silyl protecting groups. There are actually entire books dedicated towards selecting the appropriate protecting group for your given molecule. We're only going to talk about TMS, so this is kind of our go-to protecting group. But occasionally, if you continue on in chemistry, you may see other protecting groups used. All right, so let's talk about what the heck TBAF is. TBAF is N-tetrabutyl ammonium fluoride. That's why we use the TBAF abbreviation, is that's a big mouthful. Essentially what this is you've got an ammonium cation with 4 butyl groups coming off. So it looks a little bit like a spider. What does the N mean in front of tetrabutyl? Does anybody know?
Oh, that's right. It's like cutting off the end.
So do you guys remember when we were talking about butyls and naming butyls? We said that there's isobutyl, there's sec-butyl, there's a bunch of butyls, right? N just refers to it being a straight chain unbranched. So if you ever see something like N-hexane, it just means it's a straight chain hydrocarbon. It's not branched in any way. So that's our N-tetrabutyl ammonium cation. And then we just have fluoride floating around as a negative charge. So this is a really nice reagent for removing any of those silyl-based protecting groups.
Kind of like one of our catalysts.
Yeah,
Starch catalyst. Is that what
it's similar to a lot of phase transfer catalysts. Oftentimes these alkylated ammonium salts are very, very amphiphilic. They'll go into both aqueous and organic layers. So tetrabutyl ammonium fluoride is a nice reagent.
And it's also used for when you have amines, right? When you have like N-dimethylamine or something like that.
Yeah, that's a capital N. So when you're naming amines, you use a capital N to designate the substituents coming off the nitrogen. We'll get there next term, though. All right, so let's continue on. And let's talk a little bit about some review. But before we do, are there any questions with substitution or protection chemistry? No? I don't know if you guys are tired or overwhelmed today. You guys are very quiet. Tired? All right, so we'll do a little bit of review. Now we're going to talk a lot about reactions involving alcohols, so using alcohols as a starting material, converting them into something else. And we've already seen this a bunch. We've seen SN1 chemistry with alcohols. So for example, if I've got this alcohol and I want to convert it to an alkyl bromide, what reagent should I use if I want to do this through an SN1 route? Let's try to do it the easiest way possible. So HBr, right? You protonate it, turn that water into a good leaving group, it'll fall off, and then your bromine will attack in. So you could do this easily with HBr. That works well as long as you've got something that will go through a stabilized carbocation intermediate. We can also do a bunch of SN2 chemistry with alcohols. So let's discuss ways where we could get a bromine installed, and let's try to do two different ways for this. How could we get bromine or an alkyl bromide from an alcohol via an SN2 route? We know two different ways. Tosyl chloride. So we don't have a good leaving group, so we could tosylate it. So tosyl chloride and pyridine. We'd convert that alcohol to a good leaving group, and then what else would we do? We don't have our bromine on yet. Yeah, NABR, some sort of bromine salt. Alternatively, if we want to do this super easy one pot, we could just, again, throw HBr at it. Right? In this case, if we protonate our alcohol, it won't fall off on its own, but it can act as a leaving group, and the bromide can attack the backside and shove it off. So either one of these routes can work well. This works really well for making alkyl bromides. However, if we want to do the same thing with an alkyl chloride from an alcohol, we have to do things a little bit differently. We can do this using the tosyl chloride method, or we can throw HCl at it. However, if we use HCl, we also have to use zinc chloride. The zinc chloride in this case will act as a catalyst, and it will allow this reaction to occur more readily. One problem with this, though, I'll put a little asterisk over here, is this only works with water-soluble alcohols. Does anybody know why? Think about our catalyst here. Zinc chloride, do you think that's going to be soluble in anything that's non-polar? Probably not. It's ionic, so this will only work in an aqueous or protic solvent. As soon as you get into long-chain alcohols, they're no longer water-soluble, and the zinc won't dissolve and can't act as a catalyst anymore. So this is a really limited reaction, but it's one that's presented in your book. So that's one problem. The other problem is, let's say I've got this reaction. Oh. What will our product be? Rearrangement, right? So if we protonate the alcohol, it could pop off, form a secondary carbocation, and then undergo a hydride shift, which means this reaction can be somewhat unreliable because it can undergo rearrangement. So those are two main problems with the reactivity of alcohols, but I'll show you guys a good workaround. So let's do some new reactions. So let's say I've got this alcohol and I want to turn it into an alkyl chloride. I could do the HCl and zinc. However, that's pretty limited with the alcohols you can use. It only works with the water-soluble alcohols. So more common is chemists will use thionyl chloride, so SOCl2, and then pyridine. So pyridine, I just abbreviate PYR. That was the same base we used when we tosylated an alcohol. The other method that's really common, if you want to form an alkyl bromide, is you use phosphorus tribromide, so PBr3. So both of these methods work. They both go through SN2 mechanisms. So let's make a note that they both go through SN2. So what's something else we have to consider with SN2 that's really important? What's the solvent? So in this case, we've got to use pyridine. So pyridine is usually the solvent for the thionyl chloride. Stereochemistry, right? So if we have this reaction occurring at a stereocenter, we're going to invert that stereocenter too. So that's another important thing to remember. All right, so now let's do our thionyl chloride mechanism.
Does it work for diols too?
For what?
Diols.
Yes, you could do this with diols. All right, so let's take a look at this. We said already that this is a bad leaving group, which means we need to turn it into a good leaving group. We could tosylate it if we want to, but thionyl chloride is a good way of converting this into a nice leaving group. So thionyl chloride, has sulfur double bonded to oxygen with two chlorines coming off. And if you think about this, this is a really, really, really strong electrophile. It is one of the strongest electrophiles we will see in organic chemistry. This oxygen is going to attack the sulfur, and it's going to kick electrons up onto the oxygen. All right. At this point, this intermediate is really, really unstable. This oxygen, however, will clamp down, and then it will kick off one of these chlorines that's attached onto it. That will reform that sulfur-oxygen double bond. And then at this step, we're not quite ready. We need to deprotonate that alcohol. So we're going to use that pyridine solvent. This nitrogen is a good base, but it's not a good nucleophile. So it's going to grab this proton and give us our neutral product. Now the good thing at this point is we've got a great leaving group. And I'll show you guys why. So if you noticed, on this step, we kicked off a chlorine. So this chloride is actually going to still be floating around in solution. And in this step, this chloride is actually going to be a nucleophile. So this chloride is going to do a backside attack. Oops, let me do this in red. Just like we saw with our SN2 reactions, and it's going to kick off our leaving group. And the reason this is such a good leaving group is that when this leaves, this bond's going to clamp down, and then we're going to kick off our chlorine all in one step. So let's take a look at the product we would get out. So our main organic product is going to have that chlorine covalently bound to that carbon. And then what other products are we going to get? Yeah, sulfur dioxide. And then we would also have that chloride that got kicked off in that last step as well. The reason this is a super good leaving group is that sulfur dioxide is a gas. It's a super duper stinky gas, but it's a gas. So if you think about this, the gas is going to bubble out of solution and it's going to help drive the reaction to completion. So anytime you can liberate a gas, you're typically going to push the reaction in a forward direction. It's taking advantage of Le Chatelier's principle. So you know this reaction works if it stinks real bad. Does that make sense?
What happens to that chlorine?
This chloride, that just gets removed during a reaction workup. So if you think about the conjugate base, or a conjugate cation anion pair, you still have this ammonium salt, or sorry, pyridinium salt, and then you've got chloride, so you'll have to do some sort of reaction workup to remove that cation and anion. A few students will ask me this every year, and they'll say, why the heck are you teaching me this? Why can't I just tosylate it and throw sodium chloride at it? Truth is, you can, but this is a really valuable tool for some situations where tosylation won't work, so it's a nice alternative to avoid doing that tosylation procedure. However, it's equally as effective. All right.
What was that thing called again? Sulfur and oxygen.
Oh, the starting material?
Yeah.
This is called thionyl chloride. That is our super strong electrophile reagent. And we're actually going to use this later on in the year.
So does the NYL suffix of that just mean it double bonded to oxygen, like carbonyl, thionyl?
Yeah, we're not going to get into the naming of a lot of these sulfur compounds, but they typically go off of very traditional old names.
For the second step, shouldn't that be an equilibrium? The top right?
Are you talking about...
No, because the group falls off.
Yeah.
Okay.
Okay. All right, so now let's do the phosphorus tribromide and see the alternate route for installing bromines. So we just did the mechanism for SOCl2. All right, this one's pretty similar. We're stuck with an alcohol. We know that this alcohol's got a bad leaving group. So we're going to react this with phosphorus tribromide, which again is a really, really good electrophile. So this alcohol is going to attack the phosphorus and kick off a bromine, or a bromide, I should say. And then we've got Br minus floating around that was kicked off during that first step. At this point, this is a really, really good leaving group. So this bromide can actually act as a nucleophile, do a backside attack, and then kick off this oxygen. and you're left with your phosphorus waste byproduct. So this is a really nice way of installing a bromine without going through that tosylation route that we previously covered. But it is important to remember that your stereocenter will be inverted if you have one. Does that make sense? All right, let's do a little bit more review on reactions of alcohols. So we just did substitution, but let's review elimination. And I'm going to write this down, review chapter 8 if rusty. I'm not going to waste time going through the mechanisms because we already did a bunch of these. But let's do E1 with alcohols. And let's assume I've got a tertiary alcohol and I want to do an elimination reaction and form an alkene. What reagents do I need? Magic fairy dust and turn around 3 times. Yell at it until it leaves. Acid and heat, right? So anytime you've got a secondary or tertiary alcohol, you can throw acid at it, something like sulfuric acid, phosphoric acid, and then heat it up. That's similar to the cyclohexanol to cyclohexene reaction we did in lab. So let's just write H2SO4. And this is catalytic, and then heat, and that will drive the elimination reaction. Why don't I want to use dilute sulfuric acid? Yeah, Le Chatelier's principle will push it back towards the alcohol side. So remember, we could do addition to alkenes and go back to our alcohol, but in this case, we want to do the elimination. If we want to do an E2 reaction, then we're a little bit more limited. So let's say I want to do an E2 of this alcohol and form an alkene. What reagents should I use for the E2? I can't just throw a strong base at it because that would deprotonate my alcohol. What do you guys think? So remember, with E2, you have to have a good leaving group. How can we convert that alcohol into a good leaving group? Yeah, you could tosylate it. You could turn it into a bromine. You could turn it into a chlorine. We've now got a bunch of ways for converting alcohols to a good leaving group. So pick your poison. I'll just go with our trusty old tosyl chloride and pyridine. However, you could use thionyl chloride and pyridine. You could use phosphorus tribromide. You could use HBr, whichever one you want to convert that alcohol to a good leaving group. And then in step 2, now we treat it with a strong base. And again, kind of pick the base that you're most comfortable with, but we'll go with sodium hydride here because that's a nice non-bulky, non-nucleophilic base. Does that make sense?
You don't need to write down that you're treating it with NABR or something.
Sorry, say that again?
Oh, sorry, I'm thinking SN2. Never mind.
Okay, sorry. Yeah, for this one, you just need to convert that alcohol to a good leaving group. Yep.
I'm just curious, is there any difference between using a comma and using the dot when we're writing tosyl chloride and pyridine? Like, are we using those together at the same time? Are we adding tosyl?
Yeah, a comma just means that I'm giving you a list of different reagents that are all going into the reaction mixture. So tosyl chloride's one reagent, pyridine's your solvent. If you ever see that dot, this is an aside. So for example, we use a dot with BH3THF. What does that? Yeah, that dot just means it's a Lewis acid-base adduct. It doesn't mean that it's necessarily two different things being added together. It's just an adduct. Yeah, a comma just means you've got a list. A dot means it's a Lewis acid-base adduct. Okay, so now we get to switch gears to oxidation and cover reactivity of alcohols using oxidation chemistry. So let's do this. What's the oxidation state of the central carbon here? And I'm going to draw in this hydrogen because people often forget about that hydrogen. Now what's our oxidation state?
0 or minus 3. 0. Oh no, to get some hydrogen.
Oh man, we just covered this, you guys.
0.
Yep, valence of 4, right? Minus 4 gives us an oxidation state of 0 for that central carbon. All right, so if we oxidize this, I'm just going to write ox in a box. That's a loss of electrons. And when we do this oxidation reaction, we can actually convert this into a ketone. And this makes sense, right? Because what's the oxidation of that central carbon now? So valence of 4 minus 2. That would give us an oxidation state of positive 2. So you can tell we went from an oxidation of 0 to positive 2. That means we lost 2 electrons in this oxidation process. So you can convert secondary alcohols to ketones through an oxidation reaction. And then as we saw previously, you can also do a reduction reaction where you gain electrons and you go in the reverse direction. What reagent would we need to reduce a ketone to a secondary alcohol? Yeah, NaBH4, sodium borohydride. What was the other reagent that's got a little more oomph to it? Yeah, LaH, lithium aluminum hydride. So any reducing agent will work for an aldehyde or ketone. However, if you've got an ester or carboxylic acid, you must use lithium aluminum hydride. So we're going to be focusing on that oxidation step, so going from the alcohol to the ketone rather than the ketone to the alcohol. So let's take a look at some of these oxidation reactions. So let's start with a primary alcohol. And let's do a 2-electron oxidation. If we do this, we can convert this alcohol to an aldehyde. And actually, I'm going to color code these because I think it makes a little bit more sense when you think about the oxidation in terms of the hydrogens. But the oxidation of our primary, or oxidation number for our primary alcohol was -1. Our aldehyde is +1. So we've gained 2 electrons during that oxidation step. So anytime you're removing a hydrogen and its electrons, it's going to be a 2-step oxidation, or 2-electron oxidation. Can we oxidize this anymore? We have another hydrogen to remove. So we could take off that hydrogen. And if you do this, it's another 2-electron oxidation. And you can actually convert an aldehyde to a carboxylic acid. So you go from an oxidation of +1 to now an oxidation of +3. So you can see in each one of these steps, you're removing one of those blue protons. So primary alcohols, you've got a little bit more flexibility. Depending on the reagent you choose, you can actually stop at the aldehyde, or you can go all the way to the carboxylic acid. Let's take a look at secondary alcohols. Secondary alcohols have very similar reactivity. However, we've got a second carbon attached, which means we only have one of these blue protons. So if we do an oxidation reaction where we lose 2 electrons, what functional group are we going to get? A ketone, right? So if we do this, we could oxidize a secondary alcohol to a ketone. So let's compare these. We said primary alcohols can go to an aldehyde or a carboxylic acid. However, a secondary alcohol, you're a little bit more limited. You can only go to a ketone. All right, can we oxidize the ketone any further? No, we don't have any more of those blue protons to remove, or blue hydrogens. All right, let's take a look at tertiary alcohols. So let's say I've got an alcohol now with 3 carbons, and I try to oxidize it. What will happen? What functional group will we get, or will this reaction not work at all? It's not going to work at all. We don't have any blue protons. Tertiary alcohols, you can't oxidate, or you can't do an oxidation reaction on. So we'll write no reaction. All right, so now we know we can convert alcohols to ketones, aldehydes, and carboxylic acids, but let's discuss the reagents that are used to accomplish those transformations. I'm not sure if we'll go through the mechanism today. We might wait until tomorrow. I think you guys look pretty saturated right now.
With what?
With chemistry knowledge.
If you add any more, it's going to recrystallize.
Definitely not complete. That's
So for those of you that have already been in lab, we did an oxidation in lab that was a green oxidation. And I mentioned that typically oxidations are carried out using these chromium-based reagents. So this one's kind of large to draw. What's the problem with these chromium-based reagents?
Probably toxic.
Probably toxic, probably give you cancer, probably make you feel pretty crummy in the process. However, our textbook is in love with these, so I'm going to teach you how to use them. No, it was actually one of my complaints with this textbook was the first 2 editions, they were obsessed with chromium-based reagents and didn't present any of the alternatives. The 3rd edition, I just got the trial copy of, and he presents all of the new modern chemistry that avoids the use of chromium. But your guys' edition uses the old school 1950s routes. So the first thing you can do is you can use chromium trioxide, or you can use sodium dichromate. So Na2Cr2O7. If you use chromium trioxide, you typically run this using sulfuric acid and acetone, just to make it a little bit more dangerous. And if you're using sodium chromate, you typically use sulfuric acid and water. However, regardless of which combo you choose, the goal is that you're going to make chromic acid. Chromic acid is the oxidant of choice for the 1st and 2nd edition of the Klein textbook. Chromic acid will push everything to its most oxidized state when you're dealing with an alcohol. So let's take a look at what I mean by that. Actually, let's make a second note up here. We'll write super strong oxidant. And gives you cancer.
plus it's
All right. So let's take a look at our super strong oxidizing reagent. And let's say I've got this alcohol. So we've got cyclohexanol. And I'm going to treat this with sodium dichromate, H2SO4, and water. What will our product be? And we've got a blue proton, right? So if we pluck off that blue hydrogen, what functional group will we make? Ketone. Can we oxidize it past the ketone to anything else? No. So at this step, we're stuck at the ketone. Let's do the same thing with the primary alcohol and take a look at what happens with the primary alcohol. So this one will use CrO3, H2SO4, and acetone. What do you guys think will happen if we treat this alcohol with chromic acid?
It'll go all the way to the carboxylic acid.
Yeah. We've got two blue protons. So we could say, well, why don't we remove one? If we remove one, we should just stop at the aldehyde. However, the reality is our super strong oxidant is going to blow past this aldehyde and continue oxidizing it all the way to our carboxylic acid. So this aldehyde is difficult / impossible to isolate. The aldehyde is really, really, really reactive and will get over-oxidized to the carboxylic acid whether you want it to or not. Tomorrow when we come in, we'll talk about an alternate route where if we have a primary alcohol, we can use a more gentle oxidizer and actually stop at the aldehyde.